Okay, I've just written down some important information for our problem. First of all, there's the answer. At least we're pretty sure that's the answer. That's what we got by doing the triple integral. We're hoping we get the same thing doing the surface integral. We're integrating over S, which was the boundary of this half ball. So it came in two parts. We had S1, which was the right half of this sphere, and S2, which was this disk in the XY plane. So integrating over that piecewise smooth surface S means we're going to integrate over S1 and we're going to integrate over S2. Okay. So let's just start with S1. So that's the right half of the sphere of radius A. So remember, I can always parameterize a sphere by saying, hey, that's a constant rho surface. So in spherical coordinates, theta and phi would be the only two variables that would actually vary. So in general, x is rho sine phi cosine theta. But if I'm on a sphere of radius A, rho is fixed at A. So it becomes A sine phi cosine theta. Y is rho sine phi sine theta. But again, rho is fixed at A, so that becomes A sine phi sine theta. And in general, z is rho cosine phi. But again, rho is fixed at A, so that becomes A cosine of phi. So my parameterization is R of theta phi equals A sine phi cosine theta, A sine phi sine theta, A cosine phi. And let's restrict our parameters, theta and phi, so that we just get the right half of this sphere and we just get it once. Okay. So if it's the right half of the sphere, theta is going to vary from 0 to pi. Because when theta is 0, remember that's pointing straight out to the positive x-axis. Theta being pi over 2 would be on the positive y-axis, and pi would be on the negative x-axis. If we rotate past that, now we're rotating towards the left. So because I want just that half in the theta phi plane, theta is varying from 0 to pi. And phi will also vary from 0 to pi because I do want everything from straight up to straight down. So there are no restrictions on phi in order to get this half sphere. I'm only restricting theta more than I would for the full sphere. So we're actually just integrating over this square in the theta phi plane. Okay. All right, I'm going to go ahead and calculate my partials and their cross product. Now remember, every time I have a parameterization, it comes with an orientation. That orientation may or may not match the orientation that I want. In this case, I want it to be out, away from the enclosed region, so that's going to basically be rightward that I'm going to have. So you might remember whether this gives you an outward or an inward orientation. If so, great, but I still want to see the work to check, okay? And if you don't remember, that's fine, we're going to have to check. But remember, that's an important part of these problems, okay? All right, so del r del theta is going to be negative A sine phi sine theta, A sine phi cosine theta, 0. Del r del phi is going to be A cosine phi cosine theta, A sine phi sine theta, negative A sine phi. So if I take the cross product, del r del theta crossed with del r del phi, that's my symbolic determinant, I, j, k. I'm going to put this in the next row, negative A sine phi sine theta, A sine phi cosine theta, 0. And then this is the third row, A cosine phi cosine theta, A sorry, I wrote that wrong. That should have been a cosine of phi. The second component here is a cosine phi sine theta, because I'm taking the partial with respect to phi. Okay, so I'll write it correctly here. A cosine phi sine theta, and then negative a sine phi. So, when I work this out, for the i's, I'm going to get this minus nothing, so negative a sine squared phi cosine theta. For the j's, I'm going to get nothing minus this. Whoops, that's an a squared. I'm sorry. There was an a here and an a here. For the j's, I'm getting nothing minus this diagonal product, so that's going to be minus a squared sine squared phi sine theta. And for the k's, I'm getting this minus this. Now I'm just going to write what I get up here, because then I'm going to simplify it and put it here, because I don't have a whole lot of space. So I'm getting negative a squared sine phi cosine phi sine squared theta minus a squared sine phi cosine phi cosine squared theta. Both terms contain this a squared sine phi cosine phi, so I can say that's negative a squared sine phi cosine phi times sine squared theta plus cosine squared theta. But this right here, that's just 1. So my third component is just negative a squared sine phi cosine phi. So this is what I get as my cross product of the two partials. That is going to be normal to the sphere, but I want to check to see, is it outward? Because if I'm calculating the flux over the surface, it needs to be oriented outward. Or at least if I'm calculating the outward flux, it needs to be oriented outward. And if I'm using the divergence theorem, it is. Probably should have stated that at the beginning of the problem. I guess it was implied. I meant for this surface to be oriented outward. Okay. But I now need to check. So I need to pick a point somewhere on the right half of this sphere and check to see, is this going to be pointing outward or not? I think the simplest point to pick is going to be the rightmost point. I'm going to actually just draw the whole sphere, because that's easier to draw than the half sphere. If I pick this point right here, that's the rightmost point. The normal vector right there should be pointing straight to the right. Okay. But if I'm at that point, that would be where theta would be pi over 2, because that's what would have me rotating from the positive x-axis over to the positive y-axis. And phi would also be pi over 2, because that's what has me rotating halfway down to be on the xy plane, which is where the y-axis lives. Okay, so if I evaluate del r del theta crossed with del r del phi, I take that and I evaluate that at the point pi over 2, pi over 2. Let's just see what I get. Okay. Now, cosine of pi over 2 is going to be 0. So the cosine of theta here makes this first component 0. Okay. Let's see. Sine of pi over 2 is 1, and I'm squaring that. Sine of pi over 2 is 1. So I've got 3 factors of 1 here times a negative a squared. Okay. And then here, cosine of pi over 2 is going to be 0, so that third component is 0. So this has a negative y component. It's pointing to the left. This is the opposite of what I want. So, because that's the wrong orientation, I'm going to use the opposite of del r del theta crossed del r del phi as my non-normalized normal vector that I'm going to work with in this flux integral. All that means is that instead of each of these components having a negative sign, those negative signs are going to be wiped out by this. Okay. So, with that, and I do need to see this work, that you're checking that you have the right orientation. And you might have accidentally memorized that, oh yeah, if I do del r del theta crossed with del r del phi, it's going to be inward, so I need the opposite. You might have even adjusted for that and calculated del r del phi crossed with del r del theta in the first place so that you get the correct thing. That's totally fine, but I want to see the work picking a point and verifying that it works. And do remember with the sphere, you can never choose the topmost point or the bottommost point, because those are the two places where this parameterization actually isn't smooth. Okay. All right, so the double integral along S1 of f dotted with n ds. And remember, f was y. Okay. All right, so that's going to be the double integral along D, this rectangle in the theta phi plane. Y, by virtue of our parameterization, remember, was a sine phi sine theta. So I'm getting a sine phi sine theta, a sine phi sine theta, a sine phi sine theta, getting 3 copies of that, dotted with the opposite of this vector, which would just be a squared sine squared phi cosine theta, a squared sine squared phi sine theta. Oh dear, running out of space. I'm going to have to a squared sine squared phi sine theta, a squared sine phi cosine phi. Oh my goodness, this is crazy. dA. Okay, so there's my non-normalized normal vector. Oh my goodness, this is crazy. Okay, so that's going to be the double integral over D. Let's work out this dot product. So looking at the first components, I'm going to get a cubed sine phi times sine squared phi is going to be sine cubed phi. And then I've got times sine theta cosine theta. Plus a cubed. Oops. Oh my goodness, I left out a sine phi here. This was a sine phi sine theta. Okay. So I'm going to get sine cubed phi again. And then sine theta times sine theta, so that's a sine squared theta. Plus, here I'm going to have a cubed. Sine phi times sine phi is sine squared phi times cosine of phi times a sine of theta. And we're integrating that dA. Okay, so let's see. I know if I'm integrating with respect to D, I'm integrating from 0 to pi with respect to both phi and theta. Okay. I think in the interest of space, I'm just going to switch this to d phi d theta and switch this to the integral from 0 to pi and 0 to pi. All right, let's go ahead and integrate with respect to phi. Okay. Now, for these two, I've got a sine cubed phi. For this one, this is nicely set up to do with a u substitution, letting u equal sine of phi. So I'm going to break this up into two integrals. I'm going to say this is the integral from 0 to pi, from 0 to pi. Okay. I'm going to just factor out that sine cubed phi because I'm going to be integrating that same thing for both pieces. So we're going to have sine cubed phi, which I'm going to write as sine squared phi times sine phi. And that's being multiplied here by a cubed sine theta cosine theta, and here by a cubed sine squared theta. And I'm going to have to integrate that d phi d theta. Plus integral from 0 to pi, integral 0 to pi, a cubed sine squared phi cosine phi sine theta. And we need to integrate that, d phi and d theta. Okay. Now, the reason I broke this up into 2 factors of sine and then 1 more factor of sine is so that I can set this up for a u sub. I'm going to rewrite that as 1 minus cosine squared phi, and then I'm going to be able to do a u sub here with u equaling cosine of phi. Okay. I'm noticing that we've been going for a while in this video, so I'm going to stop this video here and we'll resume in the next video. Definitely easier to do this one using the divergence theorem, yes?